This video is all about performing various operations on vectors, both in algebraic and geometric settings. Please note that I'm doing these sections in a different order than the book. I prefer starting with the geometric approach, possibly because I have a background in physics, and so vectors to me carry physical concepts of velocity, force, acceleration, and other ideas that I find to be geometrically intuitive. For this video, we're going to look at this through displacement. A vector can be thought of as a description of movement. You start from the tail and move to the tip. If we're going to add vectors, we're going to do one movement followed by another. In other words, we perform the motion described by the first vector, and then perform the motion described by the second vector. The question we're trying to answer is, what is the overall movement? In this understanding, to add the vectors, we use the tip-to-tail method, meaning that the tip of the first vector becomes the tail of the second vector. Then the overall movement is the vector that points from the very beginning of the motion to the very end of it. We call this the resultant vector. There's another picture of this that you will see, which is the parallelogram law for adding vectors. For this, you put the tails together and use the vectors as the side of a parallelogram. Then the resultant vector is the diagonal starting from where the tails are joined together. This picture has a number of applications, especially in linear algebra, so it's good to be aware of it. At least for getting started, I found that more students tend to gravitate towards the idea of movement, but it's important to be aware of both. Before we talk about subtraction, we're going to talk about scalar multiplication. The word scalar should remind you of the word scale, which should bring to mind a proportional stretching or shrinking of an object, such as with maps or models being at a certain scale. Scalar multiplication is a matter of stretching the vector along its direction of motion. And for this class, scalars will always be real numbers. So if this is the vector u, then the vector 2u is what you get when you double the length. And 1/2 u has half the length. If we multiply by a negative number, then we stretch by the corresponding value and also flip the direction. With this in mind, to calculate the vector u minus v, we're going to think of it as u plus negative v. Writing subtraction as addition of the opposite is a pattern that goes all the way back to some of your early arithmetic and comes up throughout your study of algebra. So this should feel very familiar and intuitive by this point. To subtract vectors, we flip the direction on the second vector and then add as usual. We've demonstrated that here with the tip-to-tail method. There are other geometric methods out there that do tip-to-tip and other things like that, but I found that students tend to get confused because there are too many different rules to remember. So I think it's best to stick with one method for addition and work with that until you have more experience. Now that we have established the geometric framework, we're going to use that to think through the algebraic framework. Let's draw some vectors on a coordinate grid and write them out in component form. If we were to add them together geometrically using the tip-to-tail method, it would look like this. And if we look at the resultant, we can see that the total x movement is the sum of the individual x movements, and that the total y movement is the sum of the individual y movements. And this observation allows us to write down an algebraic formula for the sum of vectors when they are written in component form. To add vectors in component form, we add together the corresponding components. Using the same idea, we can look at the case of scalar multiplication. If we double the length of the vector, we double both of its components. And this is a general pattern for multiplying a vector by a scalar. Each component gets multiplied by the scalar. In many ways, this behaves like the distributive property, and we'll see more about that later. When it comes to the algebraic manipulation of vectors, there are some important vectors known as the standard unit vectors. These are the building blocks of all our vectors and are an extremely important conceptual and computational object to have. In 2 dimensions, the standard unit vectors are the vectors 1, 0, and 0, 1, which are denoted by I and j. We like these vectors because they allow us to take vectors written in component form and rewrite them using a more natural algebraic notation using some basic vector operations that we've developed. The vector AB in component form becomes AI plus BJ. This manipulation is helpful because the I and j vectors behave exactly like you expect they would with respect to the algebraic operations of addition, subtraction, and multiplication. Here's another way to see that adding vectors should be done component-wise. If we first rewrite the vectors in terms of the standard unit vectors, our algebraic experiences strongly suggest that we combine like terms, and that leads us to the same result as before. This also helps to explain why multiplication by a scalar should distribute across the components. When we write this out in terms of the standard unit vector, it's literally just the distributive property. In 3 dimensions, we have 3 standard unit vectors, I, j, and k. All of the ideas that we developed for two-dimensional vectors will work with these three-dimensional vectors. If you can add and subtract two-dimensional vectors, you can probably figure out how to add and subtract three-dimensional vectors. You can probably also figure out how to multiply a scalar by three-dimensional vectors. There are also higher dimensional versions of this, but we're not going to go there in this class. You might have noticed that we didn't talk about division by a vector. It turns out that you will never divide by a vector. We also didn't talk about multiplying two vectors together. That one turns out to be a more complicated idea that will have to wait for another section. In the next video, we're going to pick up the idea of the algebraic properties of vectors and investigate the magnitude of vectors.